Hello guys and welcome to another calculus video. In this video we're going to be taking on this awesome integral that you can see on the screen using some cool tricks and awesome formulas. So let's go ahead and jump right into the integration. So the first thing that I want to note here is that we're going to use a little bit of a rule that I follow when I am doing integrals. So that rule is when you see ln x on the bottom, oh sorry, I don't know why I have the red pen here. When you see ln x on the bottom, that means one of two, oh my god, it's still red. That means one of two things. Either we're going to be substituting u equals ln x, which doesn't really work in this case because we don't have a 1 over x for our differential, or we're going to be rewriting something as an integral. And the reason for that is the only way you can really get an ln x on the bottom, naturally, is when you're integrating x to the alpha with respect to alpha. And this is going to give you x to the alpha over ln x plus c, right? So in this case, what we're going to try to do is rewrite everything as an integral, interchange the order, and then figure out a way to integrate it naturally. So let's go ahead and jump right into that. So the first thing we're going to do is we're going to factor out that 1 over ln x that everything is being multiplied by. So we're just going to have x minus 1 over ln x minus 1 times dx over ln x times x squared plus 1. All right. So we're going to use our trick that we just talked about to rewrite this as an integral, and this is going to become the integral from 0 to 1 of x to the alpha d alpha. And then if we want to be able to interchange the order of integration, we want the integral to cover all the different terms in the integrand, right? So that means we also need to deal with this. But luckily, since we're just integrating from 0 to 1, we can just write that as the integral from 0 to 1 of minus 1 d alpha. So we can rewrite this all as the integral from 0 to infinity of the integral from 0 to 1 of x to the alpha minus 1 d alpha times dx over ln x, x squared plus 1. And now, the cool thing is that this is actually almost exactly what we just had 1 moment ago. If I go ahead and bring in this ln x, which we can totally put inside since x is constant with respect to alpha, now we have another situation just like this. So let's go ahead and plug that in as well. We're going to get the integral from 0 to infinity of the integral from 0 to 1 of the integral from 0 to alpha of, I guess I'll use beta, why not, right? X to the beta d beta d alpha dx over x squared plus 1. Now let's go ahead and just bring the x integration all the way inside so that we can deal with that pretty easily. So we're going to get the integral from 0 to 1 of the integral from 0 to alpha of the integral from 0 to infinity of x to the beta over x squared plus 1 dx d beta d alpha. So this integral of x to the beta is actually very straightforward and simple to do. We're just going to use our well-known integral formula that I proved in many videos, which is the integral from 0 to infinity of x to the k over x to the n plus 1 dx equals pi over n cosecant k plus 1 over n times pi. So what that's going to look like in this case is our value of k is just beta. So we're going to get, and our value of n is just 2. So pi over 2 cosecant of beta plus 1 over 2 times pi, which is the same as pi beta over 2 plus pi over 2. And one quick, oh geez, I can't talk right now. One quick glance at the graph of cosecant of x will convince you that the graph of cosecant of x plus pi over 2 is just secant of x. So we can just take out this plus pi over 2 and replace this cosecant with just normal secant. So we're going to get pi over 2 secant of pi beta over 2, and all of this is d beta d alpha. And notice that this is the derivative of this, so we can just go ahead and integrate normally. I'm going to go ahead and make some more space. So we're going to use the fact that the integral of secant of x dx is equal to natural log of secant x plus tangent x, or more succinctly, or more usefully rather, integral of ln 1 plus sine of x minus ln of cosine of x. Pretty easy to show both of these are true, so I'm not going to go ahead and prove that yet. So we're going to end up with the integral from 0 to 1 of natural log 1 plus sine, we're going to get pi over 2 alpha, plus natural log of cosine of pi over 2 alpha, all d alpha. So naturally, in this case, we're going to sub u equals pi over 2 alpha. So 2 over pi du equals d alpha. So we're going to get 2 over pi times the integral from 0 to pi over 2 of natural log of cosine of u, which is something that's very well known and we've proven in previous videos. So this just evaluates to negative pi over 2 ln 2. And then we also have a less familiar integral, which we can go ahead and prove the value for super quick. So let's go ahead and do that. We're going to get pi, or again, 2 over pi, integral from 0 to pi over 2 of ln 1 plus sine of x dx. And we'll call this I1. Let's go ahead and prove the value of I1 and figure out our overall integral I. So I1 is the integral from 0 to pi over 2 of ln 1 plus sine of x dx. And notice that this is the same as cosine of x, just using King's property. Now what we're going to do here is define a separate integral j, because this is going to help us out a lot. We sort of define a separate integral j equal integral from 0 to pi over 2 of natural log 1 minus cosine x dx. Hopefully you see where this is going. When we do I plus j, we're going to get the integral from 0 to pi over 2 of natural log of sine squared of x, which is just 2 natural log of sine of x, right, dx, and that's just going to become negative pi ln 2. And if we do I minus j, or actually in this case, yeah, we're going to actually do j minus I. I think that's going to help us out more. We're going to get integral from 0 to pi over 2, natural log of 1 minus cosine x over 1 plus cosine x dx, which, using our half-angle identities, is the integral from 0 to pi over 2 of natural log of, it's going to be 2 natural log of tangent x over 2. So we're going to get sine squared over cosine squared dx, and then that's going to end up becoming 4 times the integral from 0 to 1 of natural log of u over u squared plus 1 after some quick substitution du. And once we expand this as a power series and integrate using Feynman's trick, we'll figure out that this integral goes to negative g, where g is Catalan's constant, so this is going to become negative 4g. And if we want to solve for our value of I, we're just going to take I minus j and then subtract j minus I, or I plus j and then subtract j minus I, and we're going to end up getting the value of 2I, which is equal to negative pi ln 2 plus 4g, and then simplifying everything, we're going to get that I1 equals negative pi over 2 ln 2 plus 2g. So if we go ahead and look back, we had I equals 2 over pi integral from 0 to pi over 2 of ln 1 plus sine of x minus ln cosine of x, right? I believe that's what we had. So overall, we're going to get 2 over pi times negative pi over 2 ln 2 plus 2g, and then this is going to end up being positive pi over 2 ln 2. Cancel, cancel, and overall, our answer is 4g over pi. I hope you guys enjoyed watching this awesome video. We got to prove all our lemmas today, so that's really exciting. I love being able to show you guys the magic behind all the nice little lemmas, because sometimes it can be confusing. So yeah, I hope you guys enjoyed the video. I had a lot of fun, and I hope you guys did too. See you next time.